All right. Well, it is Q&A Friday, and I'm about 3 minutes early. I figured I would, I'm just getting set up here, trying to get organized, and thought I would just go live while people get on cue, because we're going to work through a few really cool questions, I think, if I might say so myself, on 1077, and those are remember, a 1077 device is supplementary protection. I don't know why I can't remember supplemental protection. Supplementary protectors, they're not a standard circuit breaker, they are supplemental protection. So we're going to talk about supplemental protectory devices, and then I'm going to lump these next two together. Is the same principle of opposing magnetic fields, pushing, and contacts. And I've got that material. And then polo neutral to a fire pump. I'm just going to tell you about that one, probably towards the end of this session. So I'm going to hit 1077 devices. I'm going to move my way into helping you understand current limiting devices. Ooh, I got a nice little breeze coming through. I'm on my side porch. We're going to talk current limiting devices, whether or not a power circuit breaker and an insulated case circuit breaker are current limiting. That's going to be a good discussion. And then we're going to talk about the interrupting ratings of overcurrent protective devices. And we're going to talk about the interrupting rating, how circuit breakers are tested per UL 489, which I think is pretty consistent with regard to fuses. So we won't get with an hour. We're not going to have a lot of time to get through that, but we'll talk about how those breakers are tested, and we'll talk about X to R ratios, and then we'll hit the fire pump. And there was another one about a barrier and 70E. I'm going to try to talk about that as well. Maybe I'll hit the fire pumps first, and I'll leave you with the question of, my 70E book is downstairs, but I'll bring it up online. Barriers. All right, it's 1:15. I said 1:15. I wanted to make sure that, and I can't see comments, so I hate that. My connection point is wasn't there, so I'm going to call it up here. So, whoop, up. All right, there we go. All right, so at least I got. There it is. See you in an hour. All right, Phil Heidi, thanks for joining in. And that was an hour ago. He said, "See you in an hour," because he probably tuned in at 12 for Q&A Friday. Oh, that was on that one. There we go. Well, where's that one at? Where am I at? Okay, so all right, so let's do this. There it is. Okay, now first things first, I'm wanting to I'm going to cover today's session is Q&A Friday. So welcome to Q&A Friday. I really appreciate you dialing in. There we go. We got Felix Sandoval in the house. Arvin Salvador, thank you. Philippines in the house. We got Colombia, South America in the house. Mr. DNS got a question on breaker isolation. Oh boy. And then Nihad, thanks for joining in. Okay, Mr. D. I'm Mr. D too. All right, so let's talk. First things first. So here's the first question that I had, and I can't remember who had. I think it was James who asked this, and it was on my YouTube channel. He says, "Do 1077 devices have only thermal overload, or both thermal and magnetic like a UL489 device would have. Hey, we got Egypt. No, Felix. Felix Nihad is over there in Canada, so he's back from Egypt. But we will still consider we have Egypt represented. So Nihad, thanks for joining. So we got 4 countries right now represented, which is kind of cool. Okay, so 1077 devices, and I gotta pass this material up here. So hold on. Well, first of all, no, let's do this. 1077 devices. That is right here. So I have a here we go. I'll show you what I'm looking at. This is this is an Eaton product guide for UL489 and UL1077 DIN rail mounted miniature circuit breakers. So let's just scroll down, because the question is asking, from a protection perspective, we know in a UL489 device, it's a thermomagnetic circuit breaker. So we have the overload region on a trip curve, and we have an instantaneous function. Well, the instantaneous function acts to open high fault currents, and the overload region, that long time pickup, acts to clear overloads and lower current type of applications. So the basic question was, he's asking, first of all, what's the trip curve look like? I mean, it's the essence of his question. When he says do 1077 devices have only thermal overload or both thermomagnetic? So he's really talking about the trip curve. This is what I would call the trip curve. It's this is the time current characteristic curve. So across the bottom we have current, and up the horizontal we have time. For increased levels of current, you have faster clearing times. So now his question is, and this is a trip curve for a 489 DIN rail mounted branch circuit breaker. Now we say it's a branch circuit breaker because, per the National Electrical Code, we can use this device to protect branch circuits. The UL1077 device, since it's not listed to UL489, is not technically a is not a branch circuit over current protected device, so you can't use that to provide protection for your branch circuits. So I just want to. I want to see questions as they come in. So I don't know. I hate this not seeing questions. So bear with me. All right. Hey, we got Tennessee, another country represented. Awesome, brother. Tennessee whiskey. Okay, so we're going to scroll down and we're going to take a look. Now, these are all the trip curves for 489 devices. You'll notice we have the long time pickup, and then we have an instantaneous region down in here, right? So what we're going to do now is we're going to scroll down till we get to 1077 DIN rail supplementary. So these are 1077 devices. And where are you going to see a 1077 device? You're going to see it in like HVAC equipment, industrial control panels. These are meant for control type of environments where you have a 1077 type of device that is either there to provide local isolation and some level of protection, right? But all of these devices, 1077 devices, are going to require an upstream branch circuit over current protective device to either provide protection just for that branch circuit that's coming down to that piece of equipment, or possibly to give you a short circuit current rating or an interrupting rating that you need for that device. So that device is not necessarily capable of those very high fault currents, and it needs a big brother upstream. So in any case, let's take a look at what the technical guide tells us. So typical applications: supplementary protection, control circuits, we already talked about that, lighting, Never thought about that one, did you? Business equipment. I was going to say business development, business equipment. And when I hear business equipment, I might be thinking, I don't know, business equipment, maybe printers, copiers, things like that, and appliances. So those are the type of equipment where you'll find supplementary overcurrent protective devices that might be a 1077 device. They're listed to UL 1077, CSA C22.2, number 235, and also IEC 60947-2. Those are your different types of different standards for different countries, and we've got a few of those countries represented. They do have accessories. Look at this: field installable shunt trip and auxiliary switch subsequent mounting. So there's accessories to it. Now, this is not quite what the question was, but I want to give you the understanding of what a supplementary protector. It's not, these things can be kind of complicated. They can have functions and features to them, less like this. They're typically DIN rail mounted. I will say typically, not necessarily have to be. All right, what else? They have captive screws. This is just trip-free design. Thermomagnetic overcurrent protection. Thermomagnetic overcurrent protection. And what that immediately tells you, what that immediately tells you is that this device is going to have an instantaneous region. That's the magnetic. And it's going to have an overload region. That's the thermal. So it will provide thermomagnetic protection of whatever is connected to its terminals, but it's not a branch circuit overcurrent protected device because it's not listed to UL 489. Let's see what else. Let's take a look. There's what these puppies look like. You'll see this type of a form factor. They don't have to be that type of a form factor. This is one manufacturer's example. But I think quite often those devices. Now, if I would scroll back up in this document, you'll see a device that looks exactly like this, but it's UL 489, not a 1077. And to answer the specific question, it does have a thermal and they do have an instantaneous. They're just like a regular circuit breaker, but these are listed in such a way they need Big Brother to help them. They're not going to be a branch circuit overcurrent protected device. These are going to be found in industrial control panels, and other type of similar equipment that we just already talked about. They can provide local things to turn on and off. They do provide a level of protection, but again, not there to meet National Electrical Code requirements with regard to branch circuit. Are available with 6 different tripping characteristics: B, C, D, K, S, and Z. Definitions for each trip curve are contained in the ordering pages. Hey, you got to order one of these. I would say you should just get a few of these just to have them around the house. I mean, you should just have them around the house. They're good conversation pieces. And if you're in education, you should have a supplemental protector that you can show to your students and describe the difference between these types of devices and standard thermomagnetic circuit breakers that are listed to 489, because that's a common mistake that occurs where they accidentally try to use these types of devices to meet the requirements in the National Electrical Code. Even though not recognized by the NEC or CEC for supplementary protectors, even FAC devices are current limiting. Okay, which means that they interrupt fault currents within 1/2 cycle. So these devices, because of that instantaneous region and how fast, and look where they start this curve. They don't start it at 0.01 seconds where you would typically see a time current characteristic curve start. They start this at 0.0005 seconds. Now, a lot of people have a misconception to think that all trip curves start at 0.01 seconds or 0.01 seconds because that's where they see most TCC curves. In reality, manufacturers do provide data below that 0.01 second line. We just elect to ignore it in many cases for a lot of different reasons, which I'm not going to get into. All right, and look at the ampere ratings, down to 0.5 amps, all the way up to 63 amps for this specific manufacturer, for this specific catalog number. And, Eaton or no equivalent. That's the way I go. That's the way I fly. 1077 DIN-RAL supplementary protectors. Look at that curve. So resistive or slightly inductive loads, designed for resistive or slightly inductive loads. Why is that important? Think about, and we're going to get into that when we talk about interrupting ratings, the X to R ratio. Okay, that DC offset, that asymmetrical sine wave stopping the flow of that first half cycle is the hardest part for some of these, for these overcurrent protective devices. All right. Oh boy, I got comments coming in. Hold on. Jeez, oh man. I get my glasses. IEEE standard 1584 for arc flash states that only the upstream protective device can be counted to provide arc flash protection if there's no barrier between the line side and load side. This is because a fault on the load side could jump to the line side. Yep, when performing arc flash studies on an MCC, I always consider that the main breaker is not isolated. It gives me more, okay. Is that a correct assumption? Given how most MCC main breaker sections are constructed, are there MCCs that provide full isolation? We're going to get to that question. That's not quite on this one. Supplementary. Overcurrent protective device upstream. Yes, Felix. When you have a supplementary protector, you're going to have an upstream branch circuit overcurrent protective device. You got to, based upon the NEC. That supplementary protector, because of where it's located, is probably going to be in a piece of equipment at the end of a branch circuit. So, a huge difference on how they are tested per the UL standard. Chris Folan, absolutely. Happy Friday, kind of wise. Excellent. Happy Friday. All right. So let's just take a look a little bit more. Inductive loads. So you can see there's a wide a range of options in the supplementary protectors. Okay. 10 to 20x. And just talking about all of this. So I am going to do this. Here's what I am going to do. I'm going to do a Control-C. And, ooh, I don't know that I can. I got to be able to. I got to be able to. So let's do this. Here's what I'm going to do. I want to come out to at least to the YouTube site. So if you're out there watching on, which I think we have some people watching on LinkedIn and whatnot, but I'm going to come out to the YouTube site, and I am going to add a note, Control V. So this link that I just posted, oh my goodness, would you believe the link itself? The link itself exceeds 200. I can't put the link in there. All right. I will modify the description. So I will have to modify the description because this URL happens to be too long. So you're going to have to go back down to the description after the fact, and I'll give you a link to that page. All right, so I am going to move over to the second question. That's what a supplementary protective device is. Hopefully I answered that question of whether or not it has the overload and instantaneous. Okay, so now, two questions I'm going to lump together. What time is it? It's 1:31, so I've only gone 15 minutes. That's good. Now here's the two. I'm going to read both of these questions, and I'm going to lump these together. Is the same principle of opposing magnetic fields pushing the contacts apart and providing current limitation applicable to insulated case and power circuit breakers, or only to molded case circuit breakers? That's a good question. The second question is, and it's a little bit longer, is it true that the reduced interrupting rating that comes on a given low voltage breaker as the voltage increases is more because of asymmetrical fault current than symmetrical? Meaning, in theory, if it weren't for asymmetrical loads, faults, that interrupting ratings may be similar at all voltages to the breaker's insulation can handle. When interrupting asymmetrical current, he says there's never a true zero crossing. So a higher system voltage means a higher voltage that the breakers will be interrupting at, which gets worse with more operating voltage. All right, so I'm not sure I completely agree with everything he said, but both of these questions are, I would say, somewhat related. So the first thing I'm going to do is I want to come back to this. All right, I want to talk about the differences between molded case circuit breakers, insulated case circuit breakers, and low voltage power circuit breakers. Now, these three devices. Oh, my power. So these three devices. Geez, oh man. I love my new Apple computer. I'm streaming this on my Apple computer, my MacBook Pro. I love it. I love it. Oh, anyway, molded case circuit breakers, insulated case circuit breakers, and power circuit breakers. It's important to understand. Once you understand the fundamental difference of these three types of breakers, in my opinion, whether one is current limiting or not is answered. Oh man, and the other thing you need to know is what current limitation is. So I gotta do something. Hold on. So, and I don't think I have it. Let me do this. Current limiting. I've got to go to fundamentals. I have a fundamentals educational piece on current limitation. There it is. All right, so there we go. Control C, and I'm going to do a Control V, interrupting rating. Let's first talk about current limitation. Control V. All right, so here we go. You ready? What I'm showing right now on the screen is a waveform. I got one. So I have 1, 2, 3, 4, 5, 6 cycles of current. So I'm showing 6 cycles, and you'll notice the asymmetry of the waveform, and you'll notice that there are 0 crossings throughout, which is why I sort of hesitated when he said there's never a 0 crossing on an asymmetrical waveform. This is an asymmetrical waveform. I'll show you what a symmetrical waveform looks like. A symmetrical waveform looks like this. Okay, so this is a symmetrical waveform, meaning the humps on the top equal the humps on the bottom. So a symmetrical waveform that's what the value that we calculate when we calculate fault currents. When we're doing a short circuit study and we're doing short circuit calculations, we're calculating that value. Then you can do a couple different things. I've seen engineers, which I believe there are some IEEE standards that tell you could take 1.6 times that symmetrical ampere value to get the asymmetrical value. But in most cases, we're going to calculate that asymmetrical value based upon an X to R ratio, which we're going to get to. But current limitation is the ability of an overcurrent protective device to have a clearing time in less than a half a cycle. So that little red sliver of this entire waveform, if a device clears fast enough within that first half cycle, that's the only energy. Instead of seeing all 6 cycles, the circuit only sees that little red piece of energy. And if I just did the calculation of the area under that trip curve, which is pretty much your amount of energy that you have in that circuit, it's much less. So your operation, now you think about this, okay? One cycle, this is a 60 hertz system. So 60 hertz, one cycle is 1 divided by 60, right? And if you take 60, 1 over, 0.016 seconds. We always say 0.016 seconds, but it's 0.0167. So one cycle, meaning a half a cycle, just that hump on the very top portion of that trip curve is, divide that 0.0167 time, but divide that by 2, it's 0.0083. And then 1/4 cycle, which is right there at that peak, that is 0.00415. 0.00415 of a second. That's an important thing to remember from a time perspective, because as we look at trip curves, if my trip curve has a clearing time of 0.1 seconds, is it current limiting? Can it possibly be current limiting? If that trip curve in its instantaneous region is going to take 0.1 seconds to clear, when we know that current limiting devices have to clear within a half cycle, which is 0.0083 seconds. If my overcurrent device takes 0.1 seconds, it can't be current limiting, right? A current limiting device has to have a clearing time faster than 0.0083. That would be a half a cycle. That has to stop completely the flow of current, which means you have to cut the peak off, and that tail that comes down has to clear in less than 0.0083 seconds. Now, knowing that information, then you start looking at trip curves, whether it be a fuse or a circuit breaker, and that tells you whether or not an overcurrent protected device is current limiting. Okay, so you take a look at molded case circuit breakers. A family of molded case circuit breakers, we go all the way up to 2,500 amps. Insulated case circuit breakers, it's still a UL 489 device. It goes up to 6,000 amps, interrupting ratings of up to 150,000 amps, and as low as 800 amps, in which you could get the long time pickup to be even lower than that. We're going to look at the trip curve a little bit later, but that beast is big. And if you've been to any one of my discussions, any one of my programs, yeah, it's a great way to work on a Friday out in the yard. All right, Mr. DNS, I'm going to get to you. So if you've been to any one of my programs, you should recall that the reason I, like, say an 800 amp insulated case circuit breaker versus buying an 800 amp molded case circuit breaker, which is much smaller, probably a lot less expensive in many ways than one, versus an 800 amp power circuit breaker. Why would I pick one over the other? The challenge for a circuit breaker is not necessarily opening those contacts, because as the person who asked this question stated, we leverage the magnetic forces to open those contacts. The challenge is holding those contacts closed for a longer period of time. Say you needed your contacts closed for 100,000 amps for 30 cycles. That's a lot of magnetic forces that want to push those contacts apart. The circuit breaker that's going to hold those contacts closed for up to 30 cycles at 100,000 amps is not going to be some scrawny little, tiny little circuit breaker, molded case circuit breaker. No, you got to bring springs and beef to the table to hold those contacts closed, because you don't want chatter. You want those contacts to remain closed, and I got to bring heavy-duty mechanisms to get that done. And it's not going to be in a small format. And not only does the circuit breaker need to be braced to be able to hold those contacts closed, but the entire structure that it's in has to be braced for those high fault currents being held together for that long period of time. 30 cycles is an eternity when it comes to currents. So that's why you've got the beef. And if you just understand that, the question of whether or not an insulated case circuit breaker or a power circuit breaker is current limiting should be answered. I'm not current limiting if I'm trying to hold my contacts closed for 30 cycles. So my power breakers and my insulated case circuit breakers, by their design, are not current limiting devices. You're going to get current limitation in your smaller overcurrent protected devices. Now, Again, current limiting by definition. Do they limit current? Yeah, sure, they sure do. Can they open fast? They sure can. That's not why you bought an 800 amp insulated case circuit breaker, right? You're there because you want all those guys downstream, all those puppies downstream to do the job. You're there to hold those contacts closed so you don't have cascading events, you don't cause larger outages, you don't want to stop because of all these inrush motors and whatnot, and transformers that are all energizing in your power distribution system all at once. You don't want to trip on any of that. So you need those intentional delays. That's why you're buying those breakers at those locations. And if we looked at, so this is what he's talking about. The from a contact perspective, you'll see how what we did in some cases on circuit breakers. Most circuit breakers now have what we call the reverse loop, so that the magnetic forces, remember the right hand rule, and I know some of you out there are saying, no, Tom, it's the left hand rule, and I'm going to sit here and tell you, no, it's the right hand rule, and we're going to argue until the cows come home. In my world, it's the right hand rule, and that's the only world you should be in. Just say it. But anyway, we use those magnetic forces to push those contacts apart, let that puppy open, and that helps us get those current limiting capabilities. Do we use that same technology in other breakers? Sure, we could, yes, but I'm not being current limiting. Again, as I get further up in the power distribution system, I'm more concerned about not tripping on these high fault currents due to multiple inrush currents, multiple motor starting currents, and things of that nature. I want to let that system start. So, let's take a look at those trip curves, right? So here is we're going to look at I think it's an 800 amp, 600 amp. So here's a 600 amp molded case circuit breaker. Now you'll notice that above a certain value down here on the right, we are faster. We're that's 0.01 seconds right down there at the bottom. 0.01 seconds. What did we say one cycle is? One cycle is 1/60th of a second, 0.0168 or something like that, right? So say 0.016 seconds. That says 0.01 seconds clearing time in that instantaneous region. Up here in the short time delay region, you're at 0.1 seconds. So how many cycles is 0.1 seconds? So this is what you do. You take 1 over 60, or 61 over, which is 0.0167, right? And we said 0.1 seconds. So you take 1 over that and you multiply that by 0.1. That's 6 cycles. So 6.1 seconds is 6 cycles. And if you remember, 6 cycles, 0.1 seconds. Let's go back up. That's 6 cycles. All the blue. That's 6 whole cycles, 0.1 seconds. So that short time delay of 0.1 seconds for that 600 amp circuit breaker is not current limiting in that region, but it gets current limiting the higher you get the current passing through these devices. Now, an insulated case circuit breaker, 600 amps. So this would be like an 800 amp frame adjusted down to 600. There's your point. That's actually 0.1. There's 0.2. So you're actually around 0.16 seconds. Definitely not current limiting here, but look at the instantaneous region. Your instantaneous region is 0.01, 0.02, 0.03 seconds. That's the instantaneous on this time current characteristic curve for an insulated case circuit breaker. If I'm telling you it's going to take 0.03 seconds to open in the instantaneous region of this breaker, is it current limiting? You can answer that question. You should be able to answer that question based on what I've told you. It can't be current limiting because a current limiting device is going to trip less than a half cycle. And how fast is a half cycle? Remember what one cycle is. 0.0167. A half a cycle, 0.008. 0008. You're nowhere close to a current limiting device. So, what time is it? 1:47. So to answer this question, do we leverage the magnetic fields in any of these circuit breakers? We sure do. We sure do. We have to always consider those magnetic fields. But an insulated case or a power circuit breaker is not current limiting. That device in this instantaneous region, because of the time current characteristic, and power circuit breakers just get worse. So I'm not going to get over to the power circuit breaker aspect either. But if an insulated case circuit breaker is not going to be current limiting, power circuit breaker is not going to be current limiting either, right? So you just got a lot of room to open up, and again, our goals are different. So the current limiting devices that you're going to see are going to be molded case circuit breakers and fuses. Absolutely. They're going to clear less than a half cycle. Hopefully that answers that question. All right. Now we're going to talk about a different topic. Now I want to talk about interrupting ratings, because the next discussion point is about interrupting ratings. So, remember, an interrupting rating is the ability of an overcurrent protective device to stop the flow of current. It's the highest current that the overcurrent protective device, and I'm talking, I could be a fuse, I could be a circuit breaker, I could be a molded case, insulated case, power circuit breaker, any classification of fuses. It's not necessarily, it could, an interrupting rating could be on a switch as well that's non-fused. It's the amount of current, the maximum highest amount of current that it's rated to safely interrupt. It doesn't have to be a short circuit. Think about that. I can have a light switch. I can have a switch on a motor control center. It's the ability of that switch, the highest current. And then you have the interrupting ratings, right? So when we talk about the impact of ratings and voltage, voltage is pressure. One of the items that you have to think about when we compare an interrupting rating, we're looking at, when we do short circuit calculations, we calculate these types of currents. We calculate a symmetrical short circuit current. Felix, now this is 100% right hand rule. Thanks, Felix. I love it. So in a short circuit current, you calculate symmetrical current. The humps above are exactly the same as the size of the humps below. But that's not reality, right? But this is what we calculate as engineers. We calculate short circuit values, current values, and we will base it on a symmetrical current. Now, and then we will pick the interrupting ratings based upon a symmetrical current value. So if I calculate 50,000 amps, that's a symmetrical value that I've just calculated. And yet I will base that calculation, I will base my interrupting rating off of that symmetrical current. But then you say, well, Tom, in reality, this is the trip curve that you have. You have an asymmetrical waveform. That first half cycle is offset. We call that a DC offset. And the amount of DC that you have in the system will tell you the decay on how long it's going to take for that to be symmetrical, okay? I'm not going to get into those details and help you explain that, because I can only do so much. So that first half cycle is the doozy. And when we test a circuit breaker, we don't test it to that waveform. We test it to that waveform. Yet, when you pick the interrupting ratings, you're picking it based upon that waveform, okay? And you're going to go, well, that sounds wrong. Well, it may sound wrong, but not really. And the reason I say that is because what we will do is we pick an X to R value, which, again, your X to R ratios, typically from 5 or 6 to 1 up to 10 to 1, typically where you're at. We pick what we think is the worst case scenario. And if you look at the literature for over current protective devices based upon manufacturers, and I'm going to show you. One. Okay, so this is, and I'm going to put the link. I think I can put the link. Hold on, Control C. I'm going to put a link to this document. Control V. And this one will work. There you go. Hey, John McCamish, good to see you, brother. All right, so this is out of our consulting application guide. And you'll see that in this section is called what? Short circuit currents, general. Okay? And it's and this, if you read through this, it's going to basically tell you what I'm telling you. But look what it says. The time varying characteristic of the impedance. This is the X. X is your reactance. R is your resistance. This determines the peak of your first half cycle. It determines how long, the X to R ratio determines how long it will decay down to a symmetrical current and that rate of decay. And this is what we're talking about. And look at this. Hold on. Where is it? This is what this is. There's shortcuts. Engineers, power systems engineers will get you in the ballpark. It's as simple as that. I'm not going to get you to the exact seat because I don't need to be in the exact seat. I'm going to get you to the ballpark, and I'm going to be conservative. Okay? I'm going to be conservative. And so in some cases, we will give you a value that is a little bit bigger of a fault current than what you need, which is okay. Or if you're doing arc flash calculations, I might give you an available fault current that's a little lower than what you can expect. And, oh, by the way, I'm going to give you a little bit longer of a clearing time. Different story, different day. Look at this. If the X to R ratio is higher than the UL or ANSI standards, the study applies a multiplying factor to the symmetrical calculated value. And remember, I said it was 1.6. This one here uses 1.35, and all depends. And these are rules of thumb. But programs like SKM, EDSA, Easy Power, they'll all give you the value of X to R ratio. Now look at this. Based on the use of an XR ratio of 6.6, representing a source short circuit power factor of 15%. That's the multiplying factor. 6.6, though, is how we rate breakers. I'm looking for the adjustment factors. Industrial mean generally satisfactory to regard reactance as an entire impedance. However, this is normally permissible only if the X to R ratio of the medium voltage system is equal to or more than 25. Where is my values? Give me a second. I gotta find the value here. Because what you'll have to do, so what we do is we assume an X to R ratio value that establishes a peak value with a slope. And if your X to R ratio is different than or outside of the extreme of how we've tested it, then you need to adjust the interrupting rating of the overcurrent protective device. That's an important piece of the pie. Now, it's very rare that you will... Here we go. I think this is it. Hold on. Yeah, see, look, in that reference that I just gave you, there's even more good information in there. Look at this. They'll tell you the typical system X to R ratios for estimating purposes, right? They'll give you two-pole turbo generators, what the X to R ratio. You can a lot of times get this from the manufacturers. There's your steps. There's your determining your X to R ratio. And these are your multiplying factors. Man. I'm just looking for that number for circuit breakers. Okay, X to R. There's your X-star ratios. This is all going through. This is all in that the reference link that I just gave you. It's a really good chapter for you. And okay, the X to R ratio is calculated in the same manner as that for a medium voltage circuit breakers. If the X to R at the point of fault is greater than 6.6, a multiplying factor must be applied. And the multiplying factor, you've got to figure out what you're actual able to interrupt with that circuit breaker, because we test it with a 6.6. And if it's greater than that, then you have more X, and you're going to have to adjust the interrupting rating of that breaker. And there's your testing range. Look at this. So molded case circuit, standard test power factors. So what we do is we create a circuit. When we have a circuit breaker interrupt the current, we set a power factor, a worst case power factor. Not necessarily the worst. It's probably the worst case that you'll find. Can you find power factors? Can you find XR ratios that exceed these values? Yes, but it's very difficult. It's not very common, but it is something you need to look at. The XR test range for 10 amps or less is 1.8 to 1.73. Over 10 to 20 is 3.87 to 3.18. And then over 20 amp multi-case circuit breakers, 6.6 to 4.9. So if you have a greater than 6.6 X to R ratio, you need to adjust the interrupting rating capabilities. It's not about the number of zero crossings. It's about that first half cycle. Okay, so that's that. That's the stuff I wanted to make sure I covered for that question. Now I want to get to Mr. D, Mr. DNS, right? All right. So Mr. D says, for arc flash states that only the upstream protected device can be counted to provide arc flash protection for a motor control center cubicle if there's no barrier between the line side and the load side. This is because a fault on the load side could jump to the line side. They call that line side propagation and compromise the main breaker. Mr. DNS, when performing arc flash studies on a motor control center, what he does, he always considers that the main breaker is not isolated, and that gives him a more conservative incident energy, when conservative means a higher value. Is that a correct assumption, given how most MCC main breaker sections are constructed? Are there MCCs that provide full isolation? Oh, man, Mr. D, that's a toughie. Now, here's my thought process. You are taking the conservative approach, and I think that's good. Because you're providing a little bit more address. The moment you start to get into the discussion of whether or not there's a line side barrier, okay, so here's the issue that you'll come across. You have two things. One is you can say that you won't have line side propagation, or you will have line side propagation. If you say, say for example, you put a barrier in there and you say, look, I've barriered this, and I have no exposed electrical contacts, electrical pieces or parts. That line side bus is barriered off. I can't touch it. I can't accidentally hit it. And if I'm doing justified energized work in my motor control center, what I could say, I could give you my engineering judgment, right? I could sit down and say, in my opinion, it's not going to propagate to the line side because there's a barrier over there. In my opinion, because you're working in the last cubicle and the main is up here on this top left-hand side cubicle, that it's not going to propagate to that line side. That is just what it is, my opinion, or your opinion. The challenge is, whenever you get into arc flash, especially arc flash, you look for standards. Now, we have arc resistance standards. We have standards that help you identify compartmentalization. we have standards we can fall back on. So what you would want to do is look at the motor control center, converse with the manufacturer, and say, how is that listed? If there's a barrier, you're going to want to know, is it listed as to the standard that permits the compartmentalization? I can't remember the number off the top of my head. If it's not listed that way, if it's not at least tested that way, the challenge that you run into is it's just an opinion. Think about it. You can say, I have a barrier. I don't know of any product. I don't know of any. I know MCCs that are arc resistant. Okay, I know that. I know we have a motor control center that you can rack the breaker out of. Okay, Eaton MCC arc resistant. So we have arc resistant for increased arc flash protection. We have the ability to, we have arc vault. We have the ability to rack the bucket out. But I don't know. I mean, your question is, I think your assumption is correct. I would say your assumption is correct. And I would say your assumption is correct. You've got to go to the upstream. Unless you find a motor control center that is either listed or tested to a standard that recognizes compartmentalization. That would be my suggestion. You can, I can tell you the likelihood. I can say, but again, it's my opinion, right? And I don't know that any manufacturer would go out on that limb to say you will not have either line side propagation. That's really what you're worried about, based upon the proximity of where you're at and the equipment. It would have to be a barrier that would be listed that way. Now, the other, yeah. So, I mean, there's always options to provide arc reduction technologies and things of that nature. There's a lot of different solutions, but I would say, Mr. D, that you're taking the conservative approach, which is what engineers do. That's what we do. We take a conservative approach and we assume worst case, and we go to the upstream overcurrent protected device. And that's what we base our incident energy on. That's the safe way to do it, in my opinion. I would love to do some tests, because here's my thought process. If, and I might do these tests, if my current is in the instantaneous region of my main overcurrent protective device, line side propagation, to your point, you're saying that IEEE standard says you could have line side propagation. If I'm in the current limiting region of my overcurrent protective device and I have nothing but a spark, I mean, there's no plasma cloud, there's no major disruption of current. It's up and it's gone because I opened so fast. You don't have the plasma to do a line side propagation. And I would love to do that test. I would love to do that test. I probably will this year, maybe next year. Run that test and show that a current limiting device, especially a current limiting device, or a circuit breaker in its instantaneous region, clearing in less than 2 cycles, you're not going to have enough energy in the air to go to the line side of that main overcurrent protected device, especially if it's in a barrier. Because even if you're in a barrier, if that barrier is not listed for line side propagation, well, then you got issues there, because you can't make the claim. You can say it. You can say this is what my engineering judgment is, but engineering judgment only gets you so far on a witness stand, right? So you got to be very careful, especially when it comes to arc flash. But your conservative nature, Mr. D, of line side propagation is safe. Sorry, it has no bearing on my ability to bend pipe or ability to learn about electrical. Not R.K. Kelly. I don't know what you're talking about there, buddy. But that's okay. Bangladesh in the house. Man, we got Bangladesh. We have Canada. We have Colombia, South America. We also have Tennessee. And wait, we got another country in here. Where is it at? Philippines. We got the Philippines. Arvin. So we had a good international discussion today, and it is 2:08. I'm enjoying my Saturday, getting some work done on my side porch. We didn't get to everything I wanted to get to, but Bill Hydia. Mini snow tattoo? I don't know what you're talking about there, Phil. I love you, brother, but come on, man. I need to understand. Great way to work on a Friday. Yes, I have. You gotta see this arrangement, man. I got my side porch. You should be here, Phil, because at 5 o'clock, 5 o'clock, we're going down to a place called Berg's in Pittsburgh, Bridgeville. They have the best pizza on the face of the earth. I don't care if you're in New York and you think you got good pizza, you haven't gone to Berg's. If you're in Chicago, my buddy Jerry O'Connor, if you're out there in Chicago and you think you got a good deep dish, you need to get down to Berg's Pizza. I'm telling you, they got the best, and they've got some really good draft beers down there too. So that's where I'm headed after my last meeting, which starts at 3 o'clock today, and hopefully they get done before 5, because I'm going to be eager to get down there. But then we're going to come right back here on this side porch, and we're going to chill out and plan our week, because next week I'm taking next week off, but we're working here. I got some stuff to do in the side over here. We're going to put a nice little barrier up, and I'm going to get some work done. So what's the link for that kind of pizza, Felix? You know what I'll do? I'm going to put that up there. Berg's Pizza. Berg's Pizza. This is where, there it is, man. Pizza and wing. Control C. Here we go. You asked for it. Remember that. And this is my my best kept secret. And see, where you at? Fire pumps. Okay, I'm going to talk fire pumps real quick. All right, so I'll tell you what I did, and I'm going to put this link in there. Okay, so here's what happened to me, Phil. Here's what happened. I got an email from an individual who was asking questions about the conductor on the secondary, the conductor for the line side tap, line side going down to the fire pump controller. And they said, look, I don't need, all I need is 3 hots. I don't need a neutral. I got to look back at the exact question. The discussion was around that neutral and whether or not the grounded conductor needed to be there. And so based upon the discussion, where is it? Is it here? All right. If a service is fed with 3-phase, 3-wire load, how do you get the effective ground fault current path? So they wanted an effective ground fault current path coming from the service and saying, look, it's a 3-phase load. I don't need a grounded conductor. I don't need a neutral because it's a 3-phase load. It's there's no line to neutral loads there. So say it's a motor, right? And I need an A, B, and C, and I don't need a neutral. So where do I get my ground fault current path? And And they said, do you run a neutral out to that main disconnect for bonding of the equipment ground or not? And so, and they showed a diagram of from the NEC. So my I went back and I said, okay, hold on. I said, you can't mix up the equipment grounding conductor from the grounded conductor. The equipment grounding conductor is what gives you your fault return path. Your grounded conductor is your neutral. And I explained the difference between the EGC and the grounded conductor. So then I said, and oh, by the way, if you're coming from the line side of the service, you're going to need to pull a neutral to that fire pump controller or the fire pump disconnect, whatever that first device is, based on 250.12C. Hold on. 250.24C. So this individual said, and I wrote a nice little email, and this individual came back and said, you had me up until you have to pull the grounded conductor, the neutral, even if you're not going to use it, to that fire pump. And they said, why? And I'm like, well, I didn't put the code reference in. Or I did put the code reference in, 250.24C. And I said, that's a good question. Why? And I had a little, my brain went somewhere else for a moment. And I'm like, okay, hold on, I think you need it. So I called one individual and we had a debate. Do you really need it? And they were like, well, no, I don't think you need that neutral. I'm like, I think you do. And I don't even think I had the 250.24C. I didn't have the 250. I just said you need to pull that neutral because I just knew you needed to pull it. I didn't have a code reference. So then I figured it out because I couldn't figure out where in the code you're required to have it. Oh my gosh. So I had to make I phoned a friend and it was 250.24C because it's on the line side of the service. And if you look at 250.24C, it tells you need to pull that neutral to the first switch or panel or whatever it is. In this case, it's a fire pump controller. And you got to think if you're coming from the utility, and the utility is always going to give you that neutral, and that neutral is what's going to get you your fault return path back to the utility. But for some reason, I had that problem of trying to tie that code section. So then I talked to Tim McClintock, and I called my buddy Tim. I said, Tim, and he says, oh, 250.24C, Tom. I'm like, oh, yes, and I found it. So then I sent that down to them, and they said, well, why that doesn't make sense. Why do I need that? And I said, that's a good question. Why do we need that? And if you understand, if you think about it, you're coming from the utility, you don't have an equipment grounding conductor because you're bonding and everything inside of that service equipment. You're establishing your grounding electrode. You have your grounding electrode conductor, and that's bonded to your neutral. It's bonded to the equipment, your equipment grounding conductor. Everything is at that one spot at that service equipment. But coming from the utility, you don't tie an equipment grounding conductor. That's that grounded conductor that gives you that fault return path back to the utility, and you size that based upon the conductor, the ungrounded conductor. So 250, Kira, send me an email to Thomas A. Domitrovich at Eaton.com. And Kira, and I'll do what I can to answer your question, and we might use it live. So, and I'm telling you, and then I called my buddy Abbasi out in New York City, and I said, hey, am I thinking about this right? And he goes, oh, absolutely. You need to pull that neutral. You need to bond it in there, even if you're not going to use it. That is your fault return path. And then I called my buddy Jerry O'Connor up in Chicago, and I said, how do you guys handle this? He said the exact same thing that they do in New York with other rules, because it's all service conductors. So that's the other important thing is that is a service conductor. It connects that equipment, which happens to be a fire pump controller or a fire pump or maybe a fire pump disconnect, whatever it is, it's connecting it to the utility. And if you look at the definition of what a service conductor is, what a service is, in the National Electrical Code, that tells you you have to treat it. So just because you are dealing with fire pumps does not mean you can ignore Article 230, and you can't ignore Article 250. So 250.24C, I believe it is. Yep, 250.24C. And then if you look at the code book, if you look at 695.6, power wiring A1, I don't know how I missed this. The informational note, this is like the icing on the cake that you really had a bad day. The informational note says 250.24C for routing the grounded conductor to the service equipment. So you've got to go back and look at 250.24 Charlie. Man, I'll tell you what. Sometimes, it's one thing to just say, hey, this is what we do. But it's those questions of why. That you go, that's a good question. Why do we do that? Or, I told you need to pull a neutral, but why? And if I can't tie it back to a code requirement, then it's personal preference. So I could not find that information. I'm like, well, it's a service. So, and we walk down through the logic. It's connecting to the service. Those are service conductors. You have to follow 230. 230 is going to point you over to 250. 250 tells you this, and you can get there in the long way. Or you can go to 695.6 for power wiring, go to A, supply conductors, and 1, services, on-site power production facilities, and boom, 250.24 Charlie. Dadgummit, we got it. So, Robert from Omaha finally made it. Excellent. Thanks for joining, Robert. So anyway, so Kira, hopefully you got that. Not me. Hello, friends. We are all friends here, so glad to see you online. All right. Phil Heidi, yeah. Fire pumps, yes, we got it. So what is the link for that kind of pizza? I gave that to you. Berg's Pizza, man. I'm telling you, that place is awesome. Great pizza. Even better than a Philly cheesesteak. I'm here to tell you. If you're from Philadelphia and you love Philly cheesesteaks, you would give them up for Berg's Pizza. And possibly a Permani sandwich. All right. All right, so that was my journey on the fire pump question. It was, do I need that neutral? Do I need that neutral even if I'm not going to use it from the utility? And the answer to that is yes. Yes, you do. You got to land it in that equipment. You have to bond it in that equipment because that is your fault return path. And that's all I got to say about that. Thank you, Phil, for reminding me to talk about that. All right. Anything else? So you got I sent my email. I got my email out there so that Kira, that pizza is FBI. FBI. For, oh my gosh, Felix, what is FBI, brother? FBI. Fantastic FBI acronym. Pizza. The pizza connection, FBI.gov. What does FBI stand for? What does FBI stand for? Federal Bureau of Investigation. Oh, wait. Did I put the wrong? No, I got it. Berg's Pizza. Yep, there it is. Oh, and look. Wait, every Thursday is Miller Lite and MGD Bottles Only Day. Oh, man. Michelob Ultra. But I tell you what, they have some good IPAs down there. And they've got great cheese sticks. Mozzarella cheese sticks. Oh, man, I'll tell you what. Felix, you would say goodbye to Columbia and just live in Pittsburgh area if you could eat Berg's Pizza every day. I'm here to tell you. I'm just saying. All right. So I think did I cover everything? I know I'm over my time. I got to look at my schedule. I know I had another call coming up, I believe. All right. I'm still good. All right. Felix, you got it. That's what it appears. Oh, you got it. All right, Berg's Pizza. All right, so pizza and wing, man, it's good stuff. All right, so hopefully you got something out of today's Q&A, and we had some fun. And I did all of this from my side porch with my MacBook Pro. I have my little mini Stream Deck that has my Teach, right? And I have my web page, and I have my PowerPoint. There's my web page, which you should see Berg's Pizza right now, pizza and wings. I've got my footer eaten, and back to me again. So I got my Stream Deck set up. I got my camera set up, going straight into my computer. And when I go remote, this is going to be easy. Oh, thanks, Tom, and enjoy your week off. I will be working. Hey, John McCamish, thank you, sir, for joining in. I appreciate it. And you too, Elvin, and thanks, Nihad, and Felix, and Robert from Omaha, and Kira, Phil Hydia, and Not R. Kelly. All you guys, I really appreciate dialing in. I'm going to sign off. And next Tuesday, don't forget IEI News Live. We're going to be live. I might be all dirty and sweaty, but we're going to go live. Heck with it. So Tuesday at 12 o'clock Eastern for IAEI News Live next week. We will be live. All right, that's all I had for today. I appreciate your time. I appreciate what all of you do for electrical safety and for the electrical industry. Stay safe, and please stay healthy. All right, guys, God bless. Take care. Signing off.